We've seen then that the energy that powers the sun and other stars comes from nuclear fusion deep in the core of the star, where there's so much gravity squeezing on the matter that the temperature is raised to beyond 10 million Kelvin, and hydrogen can fuse into helium, and some small amount of the mass of those hydrogens, called the mass defect, gets converted into pure energy according to E equals mc squared. We also saw that that process couldn't happen without wave-particle duality of the hydrogen protons. But there's one more problem we need to answer, and that's this. When you're dealing with nuclear fusion and the creation of electromagnetic radiation, what form will that electromagnetic radiation be in? Remember that the wavelength, and therefore the type of electromagnetic radiation, depends on the temperature. In the core of stars, where temperatures are 10 million Kelvin, 15 million Kelvin for our sun, and even hotter for bigger stars, the temperatures are so high that the wavelengths of electromagnetic radiation generated are going to be as short as possible, and the electromagnetic radiation will be the highest energy EMR possible, and that will be gamma rays. So nuclear fusion inside stars produces gamma rays, but this is what's powering our sun, but the sun doesn't give off a lot of gamma rays, which is a very, very good thing for us, because if the Earth were bathed in gamma rays from the sun, the gamma rays are such high energy that all life would be vaporized and the planet would be absolutely sterilized down to several feet below ground. The sun, in fact, though, doesn't give off a lot of gamma rays. It gives off almost no gamma rays. It gives off mostly the visible light that you see as sunlight, which we haven't seen very much of lately, and heat, what we detect as heat, which, remember, is really the somewhat longer wavelength infrared radiation. So the question is, how do you stretch out the gamma rays that are generated in the core of the sun to the nice visible and infrared wavelengths that you get at the surface of the sun? Well, it has to do with the fact that those gamma rays have a long way to go before they get out to the surface. They're generated here in the core by nuclear fusion. The surface of the sun has a diameter of about 1.4 million kilometers. And that means that the photons of gamma rays have to travel through 700,000 kilometers before they get to the surface of the sun, what's called the photosphere. Now, that's not a big deal because they have to go 150 million kilometers to get to the Earth, but that's 150 million kilometers of empty space. This, on the other hand, is 700,000 kilometers of gas and plasma. It's kind of like trying to get through Scarborough Town Center at 4:45 on Christmas Eve. It's not an easy journey. So these photons are traveling through plasma and gas. And remember, plasma is made up of the free protons, which we've talked about, and the free electrons, which I said I'm not going to say much about, but now I will say something about them, because free electrons are great at absorbing electromagnetic radiation and then re-releasing it. So this is what the photon has to do, the gamma ray. It's generated in the core of the sun by hydrogen fusion, and then that gamma ray has to make its way through all of that plasma and all of that gas, and as it's going through, it's constantly colliding with these free electrons, getting absorbed, getting re-emitted in a different direction, hitting another free electron, getting absorbed and re-emitted in another direction. So it's going to spend about 1 million years bouncing around through the plasma and the gas of the sun before it reaches the surface. And with every collision, it loses a little bit of energy, and the wavelength gets stretched out to longer and longer wavelengths so that by the time the photons of electromagnetic radiation reach the surface, they've been stretched out from gamma rays to visible light and infrared. Now that means that when we're studying the sun, if we want to study the core of the sun, the only thing we have when we're looking at photons are things that were generated 1,000,000 years before they got to us. Remember that the sun is 8 light minutes from us. So the journey from the sun's surface to the earth takes 8 minutes. But before that, that photon has been bouncing around for 1,000,000 years. So we're not getting it directly from the core of the sun. Is there anything that comes to us directly from the core of the sun? Well, yes, there is. Remember in that diagram of the triple alpha process that there are also neutrinos being produced with the symbol nu. And neutrinos, I told you, are leptons. They're cousins of electrons. They're so teeny, teeny, tiny that what's significant about them is that they are so tiny that they almost don't interact at all with other matter. There are right now millions and millions of neutrinos zipping through your body and not interacting at all with a single one of your atoms. Now, what that means is that unlike a photon, a neutrino, which won't interact with matter, zips right through from the core of the sun at close to the speed of light and isn't affected by its journey, which means that we can study the core of the sun directly by trying to detect the neutrinos that are coming from it. Now, of course, that's going to be extremely hard because I just said to you that they don't interact with matter. Nevertheless, we have built neutrino detectors. One of them is here in Ontario. It's called the Sudbury Neutrino Observatory, or SNOLAB. And it is built inside a mine about 2.5 kilometers below the surface of the Earth. Why do we build neutrino observatories that deep? Because we want to make sure that we're blocking out all other particles that might affect our equipment and be detected. So pretty much the only thing that can make it through 2 kilometers of solid rock are neutrinos. And then down there in this old mine, we've built neutrino detectors that are basically really, really, really large pools, like Olympic-sized swimming pools, filled up with a dense fluid like cleaning fluid and surrounded by detectors. And what happens is that once a day, purely by random chance, about once a day or so, one of these neutrinos just happens to collide with one of the particles of the cleaning fluid and sets off one of these detectors. So we pick up about 1 neutrino a day using these detectors. This picture is me. I got to go some years ago on a professional development to SNOLAB. It was absolutely awesome to see 2 meters of rock, millions and millions of years of rock just zipping by in this open cage elevator, and then to see down at the bottom of that this incredibly complex scientific equipment. But that's one of the values of neutrinos, is it actually allows us to see particles that come directly from the core of the sun rather than the photons that have that 1,000,000 year journey and constant bouncing around and stretching out and processing before they get to us. Next time we'll finish off our story of star birth by looking at what happens when a nebula collapses in more than one place.